Hello, I'm Ethan. My project title is Electricity Demand Forecasting in United Kingdom, a comparative study using machine learning and AI technique. Accurate forecasting of electricity demand is critical for efficient management of energy resources and stable operation of the power grid. With the continuous development of the energy field, after renewable energy is put into use, the power supply is unstable. There are various reasons that make predicting power demand more complex and challenging. The application of smart grid technology provides more comprehensive and complete data, making machine learning and artificial intelligence technologies very potential tools. This dataset is provided by National Grid ESO, the UK's electricity system operator. This dataset records half-hourly electricity demand data across the UK from 2009 to 2024. Enable this dataset to support detailed time series analysis. The dataset is processed and contains 19 input features. Year, month, day, hour, and minute are time features that help capture seasonal and hourly change in demand. Settlement period represents the number of times recorded in a day, and this value will be reset every time a day passes. Embedded wind generation and embedded solar generation are both estimated value and represent the actual power generation flowing into a grid at that time. Embedded wind capacity and embedded solar capacity are not estimates, but represent the capacity of wind and solar power plants during planning. Non-balanced mechanism short-term operating reserve includes units not classified under National Grid ESO's generator definition. Pump storage pumping represents the demand caused by hydraulic pump storage operations, and negative values represent pumping loads. The following features with the word flow are all type of interconnector flows. The dash feature is holiday. It's a binary value that represents whether this day is a public holiday. Next is the things that the model I designed to predict in this dataset. Their units are all megawatts. National demand is a sum of meter generation, excluding generation for station load, pump storage, and interconnector export. Transmission system demand is plus additional generation for station load, pump storage, and interconnector export. England and Wales demand is just like the literal meaning, only England and Wales part. The goal of this project is to develop forecasting model capable of predicting the free electricity demand output variables just mentioned. To achieve this goal, I evaluate it and compare a number of different approaches, including traditional machine learning algorithms and artificial intelligence techniques. Let me briefly introduce the algorithm used in my project. Linear regression is a simple algorithm for predicting a continuous target value variable based on a linear relationship between input and output features. Support vector regression extends support vector machines to regression tests, modeling complex relationships by maximizing the margin around the predicted value. Random forest regression is an ensemble learning method using multiple decision trees to improve prediction accuracy and robustness up to overfitting. Neural network is a type of machine learning model inspired by biological neurons, effective at capturing nonlinear relationships. Recurrent neural network. The neural network architecture specifically designed for sequential data, capable retaining memory over previous time states. Long short-term memory is an advanced recurrent neural network variant designed to capture long-term dependencies in time series data, overcoming vanishing gradient issue. Root mean square error, mean absolute error, mean absolute percentage error, and R-squared are the metrics I use to evaluate models. The random forest model shows the best performance among all tested models. The model is configured with 200 estimators, a maximum depth of 30, and a minimum number of sample splits of 5. Its performance is good. The specific metrics are mean square error, 2504, mean absolute error, 1908, mean absolute percentage error, 7.155%, R squared, 0.8075. These results demonstrate that random forests can effectively capture complex patterns and interactions in data and are highly robust. Its ensemble nature helps reduce overfitting, making it excellent in power demand forecasting. Next is a result of a feature importance analysis from the random forest regression. It shows the importance of each feature for power demand prediction. Among them, the most significant feature is pump storage pumping, which has the highest importance score of 0.3293, indicating that the use of pump storage system has a significant impact on power demand forecasting. Additionally, month and embedded solar capacity also have high contributions at 0.2039 and 0.2023 respectively, emphasizing the impact of seasonality and solar patterns on demand. However, some features are of lower importance, such as minute and year, and have limited predictive power. This is also understandable, because data is recorded every 30 minutes. The minute feature will only appear at 0 and 30, and the year feature has a large number of samples every year, making it difficult to directly analyze the relationship between the year and the actual value. Understanding feature importance can help optimize data collection and focus on high-impact variables, thereby improving prediction efficiency and resource allocation. However, it should be noted that the random forest model provides a global importance score, which may not capture the local feature correlation under a specific period or scenario. In the process of experimenting with neural networks, I found that the difference between the model's predicted value and the actual values has increased significantly since 2020. This suggests that there may be some key factors not included in the model that lead to significant change in electricity demand. I speculate this is related to the effects of the COVID-19 pandemic, such as lockdown measures and change in behavior patterns. However, since the random forest model still performs well on the same data, this suggests that the existing features can still partially capture demand trend. Further analysis is needed to verify whether the impact of the pandemic is the main cause. In recurrent neural network experiments, I found that decreasing model capacity, such as adding more layers or neurons, did not improve performance and sometimes even lead to a decrease in performance. This may be due to difficulty training large models. Although the feature importance generated by the random forest show that features such as month and settlement period were important, increasing the time step and to capture these long-term dependencies did not consistently improve the accuracy of the RNN. For example, when the time step is increased to 10 or 1 day, which is equivalent to time step equal to 48, the model performs no better than when using a step of 1. This may indicate that the current time step is not sufficient to fully capture long-term dependencies, and I was unable to test larger time steps due to hardware limitations. The performance of the LSTM model is lower than expected, probably for the same reason. Unlike RNN, increasing the time step has a positive impact on the performance of LSTM. This is in line with the design concept of the LSTM model, whose memory unit and gating mechanism can better capture long-term dependencies. However, due to hardware limitations, I was unable to test larger time steps that would take full advantage of LSTM. That brings me to the end of my presentation. Thank you for your attention.